Okay, thank you very much, Paul. Well, here we can see an example of a system of SMA system, multi-cluster system, which is PV photovoltaics together with battery inverters and connections to the load and also to an auxiliary source. This is suitable for working in AC coupling configuration. That is, they provide an AC line and other components can be connected to that AC line as grid tie inverters, for example. They can connect to this installation. Here we can see the photovoltaic inverter can graduate the generation of power from a gradient depending on the grid frequency. This means that these inverters have the off-grid mode, which is that the battery inverters modulate the production of the PV plant by means of increasing or decreasing the frequency, and so that the PV inverters can reduce if the frequency is rising from 50 Hz to 51, 52. The PV inverters know they have to they have a ramp down to go from 100% to 0% of their production. So the battery inverters know what they have to how to manage the PV plant. If the battery is full, the load consumption is low, and the PV production is high, we have to fit that PV production to the current status that we don't need much energy. So the battery inverter raises a bit the frequency, and the PV plant reduces gradually the production. We have a high conversion efficiency, bigger than 98%, and can work in critical environment conditions, 100% of humidity and up to 60 degrees Celsius. Also, battery inverter is suitable for working with both lead acid and lithium-ion batteries. These two technologies, it is important to have the chance to use lithium batteries. And because in the future, all the systems that have lead acid batteries may be moved to lithium technology. In the case we have to replace the battery, and so this is an important point. The total number of battery inverters must be a multiple of 3. We want clusters, three-phase clusters. And so the grouping in clusters of 3, there is a main device that and 2 slaves, and they manage only 1 battery. Each cluster is a power increase. So we have the main cluster, which is managing the whole installation, the whole plant, and more clusters that add power like slaves. But there is only 1 inverter, 1 battery inverter, which is managing the whole plant. And the box in the middle, we can see the multi-cluster box can facilitate the connection of all these components. We can have in a big system a lot of devices, many inverters, many battery inverters. So connecting an auxiliary support to each of the clusters would be very complex, many wires, and so this box simplifies the task of connecting everything to this system and conforms the system with all the PV plant and battery inverters to provide to the loads. Have the protections, everything inside, and so it's easy to go and connect a cluster or exchanging an inverter, because all the connections are done in the box, not in the specific devices, battery inverters. So the maximum number of battery inverters that can be joined in 3-phase clusters is 36 or 12 clusters of 3. The maximum power of battery inverters in the installation with this technology is 216 kilowatt of Sony Island battery inverters. And considering that the maximum power that the internal transfer relay of each battery inverter can support, almost 12 kilowatt, the maximum power suitable for the cluster of photovoltaic inverters of the installation is 414 kilowatts. It means a ratio of almost 2 to 1. When designing, we always think in the PV plant can be maximum of 2 times the size of the battery inverters. So in the next slide, we can see an example. This technology of SMA is appropriate for 3-phase system configuration. Also with AC coupling and interconnected to the distribution grid. We can see here the auxiliary support. Here below in the image of the multi-cluster systems, we have an auxiliary connection to the utility grid and also to a generator. Genset both can be connected to the system, and if one fails, the other can supply. The system detects the presence of the grid, and if we have utility grid, we use it better than the generator. But if the grid goes down, it is quickly detected and it switches to the generator. So the auxiliary support is always present. Here, however, the maximum size of the system is 216 kilowatts of nominal power of battery inverters. Combined with the photovoltaic plant, it's 414 kilowatts of photovoltaic inverters. Nominal power, then we can have bigger peak power, so approximately 475 kilowatt peak of photovoltaic power. We have this limitation. We have this maximum size, so if the project needs a bigger power, we have to split in different installations. The maximum size is this one, so if we need more than this power, we will install different different installations with the same components, and that's how we install these systems.
So in the case of the SMA configuration, Ivan, meaning that if we want to reach, for instance, a 1 megawatt project, we need to install approximately 5 of these units, between 4 or 5 of these units. Yeah.
Yes, this would be the case. Also, there are other systems like hybrid controllers, which have bigger size, but it is a controller, and then you have gensets, PV, utility, and this hybrid controller manages the whole system, similar to these multi-cluster systems, but with higher sizes. In this case, this one makes possible to have an off-grid system when in the case we don't have utility grid. We can do off-grid, and in the case of hybrid controllers, now they are starting to have the possibility to do off-grid as well, but usually they needed the presence of utility. The hybrid controllers are another type of installations.
Okay. Okay, so this is the most flexible, yeah, versatile solution for interconnected mini grids that we can have from SMA at the moment, which is probably the most popular. Yeah.
Yes, this technology is very well known, and so is the easier way. In the case of hybrid controllers, is when we have bigger sizes, large scale megawatts, and to manage these central plants, bigger and or a genset plant of many gensets, to manage many units of generators, big generators, we need a complex controller, complex communications. So it's another kind, it's large scale. In this case, is better. It's very optimum.
If I may also just add one point, I mean, from the experience that we have on ground for systems up to the size that you have just mentioned here, they are also at mostly the maximum size that you can have in a low voltage distribution network. So from that point, this limit is actually not so bad. I mean, it covers pretty much to what you can go with a low voltage network as well.
Okay.
Many thanks, Imran. That's a good point.
Okay, Ivan, if you can go very quickly, because we don't have much time, to comment a couple of projects that you wanted to share, but I can only give you 5 minutes, so you have to go very quick.
Okay, let's try to. So we have here a rural electrification of 7 communities. In this case, the population is 4,800 people, but the users expected are 739, which is almost 700 households and 41 basic services. And in this case, the total investment, this is the case of isolated hybrid mini grids, and the total investment is more than $2.5 million US, and the total installed power is 219 kilowatt peak. So this is 7 standalone hybrid solar diesel generator mini grids, the off-grid classical scheme, and with diesel generators, which make it a bit expensive. And so here they had to do deep social work to promote the self-management and productive uses of energy. This is to understand how the system works and how to optimize the use of these systems. They have also a local capacity building for installation of operational maintenance tasks, and this is the case of the isolated scheme model.
This is an example of each village has its own mini grid, yeah?
Yeah, each village with own PV resources, isolated, or in this case, the strengths. It's the creation of 7 local associations to manage the mini grids. This is kind of social development. Also, a local capacity building for users, and the creation of association and training local installers to do internal consumer facilities and basic mini grids maintenance. You have to prepare people to manage these installations, and in each town you need these facilities. So the encouragement of productive uses of energy is important. Basically, electric mills, battery charging, and community refrigerators and freezers. So that's the idea. I think I've lost the image. Paul?
I am back. I am back.
Okay.
Okay, sorry, something happened. I hope everything is okay now.
Yes, I can see it again. So challenges of this kind of model is that, or in this case, for these 7 rural communities, is the compatibility with the national electrification strategy. It differs a bit of, well, there is no grid, and it's a case of isolated mini grids. The regulatory and institutional framework always it's tough in many of the places. The high investment per household electrified is important in this case. After 2 years, the connections were below the expectation, 50% only. Also, the consumer fraud is a challenge. Always there is a kind of fraud. Well, the monthly income is constant, and the lack of specialized maintenance is another challenge in these cases. There are several mini grids, and so you need trained people to maintain and do the service. In the next slide, we can see the other model of a kind of centralized electrification in the center north of Burkina Faso. Here we have electrification of 7 PV systems for 6 pumping stations, and also electrification of 65 villages. It's a big one. In total population, it means 78,000, and in number of expected users, it's 13,000. It's quite a lot. Here, the total investment is almost $7.5 million US, and the total installed power is almost twice the other case, almost 600 kilowatt peak. The main characteristic is 5 interconnected mini hybrid solar grids, standalone and grid-tie operation models. Here, the strengths are the system architecture based on private company commercially exploiting these 2 zones. One main medium voltage connection for each of the 2 eco zones. There is 200 kilometers of medium voltage distribution grid and almost 600 kilometers of low voltage distribution grid. So in this case, the innovation was the 6 mini grids can operate as off-grid and on-grid systems. This is a good point. So the compatibility with the national electrification strategy is approved, and so it's also a good point that align with the utility strategy, and a low investment per household is lower than in the other case. So here, other point like modularity of solar generation and installation of electrical pumps was strengths of this project. In between the challenges, we can see again the institutional framework is always really tough. So the high utility electricity cost as well. I have there. The performance depends partially on the utility power cuts. This is always the same. We can find here as well customer fraud, and in this case the monthly income fluctuates. Also this instability and terrorist threat in this case. So there are so many challenges in this project, but this is a case of centralized, kind of centralized model. And here in this slide, we can see the comparison between these two models. The first column is the case of a centralized model, where we can see there are a lot of distribution lines, medium voltage and low voltage, and transformers, which are expensive. So the investment is higher than in the isolated cases. Here we can see the total investment per user is very low in the centralized model compared to the isolated mini grids. The total investment is higher, but 7.5 million compared to 2.5 in the case of isolated mini grids. But the estimated users are bigger, a lot bigger. In the case of centralized, we can provide to many more users. So this means the investment per user decreases a lot in the case of centralized models. You can see 514 versus 3,500. This is quite less in the case of centralized. And thank you very much for your attention. If you need more questions on these topics, please write to me, and here you have the contact. And okay, I'm passing the floor to my colleague Imran. Many thanks.
Thank you very much, Ivan. So Imran, if you can complement that with the project experience in Nigeria on IMAS. Thank you very much. The floor is yours again.
Okay, thanks a lot. Thank you very much, Ivan, for this nice explanation of technologies, and interesting to see how the industry is also adapting to the situation on ground and the need for interconnected mini grids. I just want to, again, bring you back to Nigeria. As I said, this will be the focus of my parts today, and tell you about an interesting program that GIZ is actually implementing in Nigeria together with the Federal Ministry of Power there. I think we already saw this, that there are a lot of mini grids out there and a lot more are being planned. Just to give you an idea, integration has been working with GIZ since 2014 under the Nigerian Energy Support Program. And in the first phase of the project, we supported them with development of 6 mini grid projects. These were all off-grid projects. And now under this interconnected mini grid scheme, we are supporting in designing and implementation of 20 plus interconnected mini grids that are supposed to reach around 100,000 people. And they are basically dispersed in the country such that there are projects with different 7 distribution network regions out there. So we are working with a lot of distribution networks, discos in Nigeria, and each has different characteristics as well. But before I continue, just to remind again that these are 20 plus projects out there, and they have a very big range in them as well, how they are framed up. So to give you an idea, the kinds of interconnected mini grids that we are looking at are primarily in semi-urban areas. Some of these are also rural communities which have some grid connection. So the primary idea of this interconnected mini grids was to target those areas where there is some level of distribution network available on ground, but the supply is at the moment not good enough. And I will come back to this point, how we find out those sites. But just to show you the variation, we have communities that range from 450 connections to 3,000 connections. And as Ivan just showed us that, the size of the communities also has an impact on the technical system which is designed and the cost implications for it as well. And therefore we have systems that are ranging from 50 kilowatt peak per system, very small system. Here you have in green example of this one. And then, for example, a bigger system, which is for a community of around 2,000. And there we are looking at a system of around 350 kilowatt peak system. So in this system, we have, let's say, multiple portfolios. And those portfolios consist of, for example, one project consisting of only one site, or also consisting of multiple sites that are near to each other in a vicinity of, let's say, 20 kilometers or something. And therefore, we can have a discussion whether it should be separate low voltage systems or there is a medium voltage connecting them as well. However, in terms of the projects the sites that are out there, we see a large variation in the existing grid infrastructure. So we have systems, for example, you see on the left, a system where there is only 10% of the network, which is at the moment existing out there. This means that the village hardly receives any electricity supply from the grid. A lot of investment is going to be needed to build up the network. On the other side, you see a system where almost 70% of the network is out there. And that means that the interconnected mini project, when it is going to happen, it's going to benefit a lot from the fact that there is assets on ground which can be used, needs rehabilitation, but still can be used. There is grid supply, which we already talked about, that is a big factor in making the projects more viable. But from our portfolio, we see that the tariffs that we are looking at are in the range of around 30 cents to 40 cents. That is still because a large part of the supply is coming from the PV system and the diesel generator as well. Just to give you an idea or to, let's say, make it a bit more digestible, here is an example of a project, for example, that we have. We have a 250 kilowatt PV system with a 130 kilowatt diesel generator, and it is meeting a demand of 350 megawatt hour per year. It is for a community of 10,000 people. Just to put it in context, we have a battery storage system, which is 150 kilowatt hour. It is lower than the typical comparison of battery storage to PV system, but this is because of the strategy that I talked about earlier, that you benefit from grid supply to ensure that you do not invest too much into batteries. In such systems, we have tariff of around 35 cents. And then this system is able to save around 120 tons of CO2 per year. And this means that these projects are typical, like compared to off-grid projects, the energy and the CO2 savings are less in interconnected mini grids because you are still using grid supply as well. And then we say this system of around 1,700 connections, or for 10,000 people, it requires an investment of around 850,000. And the system that we have here is that we have typical investment of around 125,000, which is coming from an investor, and around 200 of the thousand is coming from debt. And such a system in our approximation has roughly around 40,000 operational cost per year, just to put it into perspective. In terms of how these projects are set up, the business model, basically you have a lot of actors in the Nigerian market. And I want to just put it into context. So the central is the mini grid developer, which are usually private operators who are planning to invest in such projects. Of course, there is the community, and then there is the distribution network. In addition, there is also a rural electrification agency in Nigeria, which is responsible for all such projects and for rural electrification, be it mini grids or off-grid or interconnected mini grids. And then there's also the role of third-party investors. The way it is working is that the mini grid developer would agree on a mechanism with the distribution network operator, at what rate I'm buying electricity from you, at what times you are providing me electricity. And this is the and then they're also paying a fee for using the network which is out there, because this is at the moment the DISCO has a right to say that you are using my network. So they are basically providing them a lease on it or giving rights of access. So there is an agreement for that. In addition, the mini grid operator would have an agreement with the community that we are going to build a system in your community so that we are going to provide you electricity at an agreed tariff. In Nigeria, almost in all the new cases, these are prepaid meters to provide security of payments to the mini grid developer. And then between all three of these actors, there is a tripartite agreement, which brings all of them to the same page so that there is no disparity in the relationship between the developer and the DISCO and the developer and the community. And this is very important to set up for such systems as well. This factor of distribution network is not there in typical off-grid projects, but interconnected mini grids do have this additional player of the distribution network, whether be it a centralized agency or in different countries, you will have different setups. But it is important to realize that interconnected mini grids, we will have this additional agency which needs to be considered in project planning as well. Then basically there is a grant coming in this project via the Rural Electrification Agency, which is in the backend being supported by GIZ and EU. And then, of course, the developer is bringing his own equity into the project, and whatever is remaining is coming as debt from or equity investment from a third-party investor. So this is a rough setup of the project. Well, if you will allow me, I would just take a couple of more minutes to talk about how the strategy in Nigeria is to scale up this sector.
Yes.
The idea is that, we just saw that, we have 50 systems that are out there, and around more 100 of them are going to come up. And when we talk about scale up, there are two basic questions that need to be answered. The first is, where can we have more of such systems? I mean, this is kind of also the starting point. And there we are working with Federal Ministry of Power, where we have developed like a mapping platform, and where we are collecting data about the existing grid out there and the sizes of the communities. And we do this by using remote methods like using satellite imagery, but also we are deploying teams on ground, which are basically covering the network and mapping them using digital tools, so that there is a database which can be provided to market players to show them, okay, this is what the country looks like. This is where, there is a potential to build such a system. These are the hotspots, or these are the good locations to look at. And this central database management system has option to display using different criteria. You can go on different states, you can look based on different community sizes, you can look at the high voltage network where it is available, and then it gives the investor or the market players an idea to see, okay, this is the status out there, and these are the main areas that we could focus on. And this allows them to build a pipeline for future projects. And this is very important for scaling up the sector. We have very recently launched this platform together with the Federal Ministry of Power, and you are very much welcome to go to this website, Nigeria SE for All. And there you can access this as well. It's an interactive map, and you can see it, and you can explore around and see how this can look like and how this can support. And the second question is, once we have those mini-grid projects or interconnected mini-grid projects, and after a certain while, they are not just 4 or 5 projects out there, there are a lot of them, and how they can be monitored and managed in a realistic manner to support further cost efficiencies in the sector, and also benchmarking to drive further growth in the sector. And in this side, we have worked with, again, with the Federal Ministry of Power to prepare a monitoring platform, whereby our goal is to register all mini-grids, be it interconnected or off-grid mini-grids in Nigeria on this platform. At the moment, for example, we have been able to include 35 sites. We are still collecting data on 50 more that are out there. But the idea is that such a platform allows an agency, a regulatory agency or other stakeholders out there to have a portfolio level overview, what is happening in the sector, which kinds of systems are coming, and what further support needs to be provided in terms of making these projects more technically viable, and also if there are financing gaps as well. Again, I will not go too much into the details of this, but I invite you again to visit this portal, Nigeria SE for All, where you also have this tool, this monitoring tool, where you can see how projects can be monitored on a portfolio level. So all projects in a certain region or under a certain program, or you could even go onto specific projects and see how that is looking like. And this has been actually the experience in Nigeria, that it's a booming market. It started with the first few projects, but what is important to realize is that after you have the first 2-3 projects, it's not going to continue linearly. It's going to become more exponential, because once the market is there, the prototypes have been shown, there's going to be a factor of going from 5 to 50. And then the government, the regulators and other actors need to plan for that. I think that would be also an overarching message that, the technology is out there, it is being shown and proven. And I think using of these tools is also now going to become more and more important to support further growth in the sector. And I think that would be, like I would say, the positive message coming out of Nigeria in this case. Again, happy to present. And if you have any further questions, please feel free to reach out. Happy to support. And thanks again for this opportunity to present. Back to you, Paul.
Thank you very much, Imran. And I think your words are very, very, convenient for the state in Nigeria the experience in Nigeria that you are talking us about can be very inspiring.
Happy to support.
Left because we started a little bit later than 9. So now it's time for questions, for comments.
Yeah, thank you for the presentation. My name is Kemal. I was thinking about the last presentation, not this one, the one about the mini grids on costs and things. I saw a lot of challenges there, which is a reality, I think, in many of the rural areas in Southern Africa as well. But I missed a little bit of how do the beneficiaries of these supplies pay, or if they pay anything? Who is establishing the collection facilities or collection network? And if you can elaborate a little bit more about the payments, how does it work? Payments for consumption. Thank you.
Hello, my name is Fred. I would like also to add in the same line another question. I try to compare the tariff of each user in Nigeria. It seems a bit higher, especially if we are compared with our national tariff here in Mozambique. And again, how we, of course, there is a social benefits on it, but also seems that the users, they are paying a lot for the energy. How is it? How can we deal with this effect?
Okay, thank you. Ivan and Imran, are you there? Did you listen to
Yes.
the questions? Okay.
Yes.
Any first reaction?
Yeah, I can. If we go in the reverse order, I can immediately talk about Nigeria.
Okay.
So, I mean, you are very right on this, that, you know, even in Nigeria, the tariff for grid systems is much lower. I mean, maybe by a factor of 7 or 8 times lower. But the fact is that, and this is our experience being on ground as well, that mini grids, be it off-grid or interconnected mini grids, have a component whereby they are providing reliable electricity to these communities. And for realizing such projects, there has to be a lot of background work that the developer or the agencies are approaching these communities and explaining to them that, look, you have at the moment a 5 cents per kilowatt hour tariff, but you only receive it 2 hours per day. And that means you are using very expensive diesel fuel to meet your needs at the moment. And therefore, there is understanding that there is an alternative. That means you will have to pay a premium tariff, but you would still be better off compared to using your diesel generator for that. That is the one side. The second one is that, I mean, it has to go hand in hand with the fact that, you know, the availability of electricity in these communities is not just to meet the demand for turning on bulbs and television. The idea must always be that it should stimulate local economies so that those people are empowered to generate more income and be able to also afford this. Like Ivan said, you know, a lot of communities, the issue is that, you know, the income that people have available at the end for expenses of energy is still the same, and that will not help. So this effects on this efforts on electrification must always, you know, consider this factor that there is a strong focus on enabling these communities to generate more, to have more productive uses, to be able to generate more. And then also on the financial side, there's always this comparison. What is the current expenditure on electricity? Not just the tariff that they're paying, but the overall. And that provides a benchmark. That is the first side. And then the second one that I just want to close with is that, you know, this is still a sector that requires grant support. And that means that that grant needs to kind of be evaluated on a realistic basis to say how much does the grant need to be to allow these systems to have a realistic tariff that the communities can also pay. So for example, if the grant is at the moment 60% and I have a tariff of 30 cents, but I know that this community can only pay 20 cents or 15 cents at max, that means the grant needs to increase. And this kind of project modeling and financial analysis can also help drive those policy decision making to set up such projects. Yes, is that okay? I think, Ivan, do you want to now take on?
Yeah, thank you. I think it was a good clarification.
It's okay.
It's okay. Also, thank you. Also, thank you.
Mm-hmm.
Thank you. Thank you very much. Any more questions, or not only questions? I know some of you from EDM, from FUNAE, have a lot of thinking about interconnected mini grids. If you have ideas, comments, or what are your challenges at the moment? What kind of projects are you thinking of? You can share your ideas. I think you were considering projects up to 1 megawatt, right? For interconnected mini grids. Somebody from EDM, perhaps from the off-grid team, if there's anybody, we can discuss a little bit your initial ideas. That's just a suggestion if you want. If there are any other questions, please. Now it's a good moment to ask them.
Yes, hello.
Hello.
Yes, Isaac speaking here from EDM.
Good morning, Isaac.
Yes, many thanks for the wonderful presentation all from Iran and Moreno. EDM now is pushing also the off-grid component, and we are developing 2 megawatt projects in Zumbu district. There we have a network coming from Zambia. The network is now being fed by a generator in Zambia. And as you know, the generator has many cuts of electricity during the day. And so we are planning to replace the diesel generator by 2 megawatts power plant. So we would like to know from your experience, a part of SMA technology that we are already aware that it cannot supersede 0.4 megawatts. Which technology can we put in place in order to develop such project? We are still in the early beginning stage of preparing the project. We are raising the funds, so we would like to get your support. I don't know if you can give us the best suitable technology that we can use there.
Okay, thank you very much, Isaac, Ivan and Imran. This is a question about initial ideas, yes, to replace a 2 megawatt connection from genset in Zambia. Okay, so the border project with Mozambique, and the colleague from the ADM utility in Mozambique is asking what kind of technologies, what kind of approach could they consider for a project like this. Who wants to have a first go? I think both of you said things in this respect. I don't know, Ivan, do you want to have a go?
Yes, well, in this case, the size, 2 megawatt is a big size, but in the case of SMA, they have hybrid controller systems, which were called fuel-safe controller before. And these hybrid controllers can manage the different sources, gensets, PV, and also have the ability to do the off-grid, off-grid since few years ago, 2 years ago more or less. They started the first project with hybrid controller in a plan of similar size to there were in the first phase 2 megawatt of PV plant, and then it was grown to 4 megawatt plant. And also the central inverters used have the possibility to create the grid, to work as a sunny island. So now in SMA they have the technology of off-grid systems of the classical sunny island, also in the central inverters. So in that project they were using this central inverter that creates the grid. And it was a 4 megawatt inverter, but they start with 2 megawatt inverters for this technology that can create the grid. So this could be an option, because off-grid systems, you know, the size we have seen, the size, the maximum size we can afford, and so splitting in different systems, I think, is not the idea that they have. So it could be a good idea to check the technology of the hybrid controller. Before it was called fuel-safe controller. Maybe they know some. I will check this possibility. Yeah, because you can have a central inverter producing 2 megawatt or up to 5 megawatt. This with the diesel generator disconnected for the time that the battery lasts. And then at midnight, more or less, the generator takes the lead of the grid.
Okay, thank you, Ivan. Imran, do you want to add something here?
No, I think, Ivan, I think being the SMA expert, I think pretty much covered it. I think there's just one factor that I remember about this hybrid system is, well, that when you are planning this system, I think what was also very clear from your answer, that the diesel generator still needs to be there. I think that's very important to clarify. It cannot be replaced. And secondly, there's also in such systems a limit to the PV integration. Let's say the level of renewable integration that you have in such systems. I think it is about 35 to 40% or something like this. And that also needs to be considered, that, you know, you have this system where the PV is going to replace battery. That's why it was called the fuel saver. But there are technical studies, and I think SMA also provides approaches how to do that, to estimate how much of this diesel you can actually replace. So that what I would say is that in terms of setting realistic expectations, you cannot say that you will be able to replace 2 megawatt of diesel just by 2 megawatt of PV. But there would be a certain level to it that can be done. But, you know, it would still more likely remain like a hybrid system. I think that would be just my comment on that one.
Yes, of course. And well, depending on the battery inverter, the central inverter with battery you can use in that installation, maybe you can increase that percentage.
Exactly.
They in theory they say that, well, you could go to 100%, but it's not very much realistic maybe now. But yes, it's true. It's true.
It's true. And I mean, one advantage also with this PV is also this modular approach. Yeah? So, you know, these systems are always normally designed to accommodate future expansions as well. All these technologies are as well. So maybe that's also helps in this direction.
Yeah, in this project we have seen always different phases, maybe starting with only a PV plant, then increasing that one, or adding a battery, and in several stages they have the chance of fulfilling the expectation. No?
I wanted to ask, in a situation like what engineer Isaac from EDM was saying. Okay, we know SMA has a possible solution for that with the hybrid controllers, fuel saver. But what about other manufacturers? From your experience in RAN in Nigeria and other projects, we know SMA is good reference, but what about other alternatives can we have, or even if just to give our colleague some other spectrum of other technologies they can look at.
Don't know, Imran, if you know any other alternative.
I mean, so I would not have exact name of a product, for example, from Schneider, for example, or other manufacturers like Huawei, who are now also very actively entering the market. But I would definitely say that, SMA is one of the leading one, but not just the only one. I think there are also this megawatt level solutions that are coming from Schneider most likely. And I think in Nigeria, we also have learned that Huawei is a very active player because exactly, because embedded generation is what they call it in Nigeria, that if you have projects beyond 1 megawatt, and I think in that range, you have those players out there in the market as well. But I mean, like to admit also that, the viability of such large systems, like the technical proof of concept is not very much existing at the moment. There are not too many examples out there that we can say, okay, this was a reference system, so still would take it with a bit of caution, I would say.
I could send a link to Paul for sharing where they have in YouTube a nice video of this project I was commenting in an island in the Pacific. It's pretty nice, and I will send you to have a look.
Yes, thank you. We can then share it with the audience, and especially with engineer Isaac and his team.
Yes.
I don't know, Isaac, if you have any other comment.
Yeah. Thanks, Paul. It was the explanation was clear, and I definitely think that the idea of using hybrid controller can be a superb idea solution for that. Although we need also to check another technologies to see which one is the suitable for us. In our case, the additional information that I would like to provide is that the system will also have battery storage. So we are planning to have 1 megawatt.
And the generators are several generators, or it's only one unit?
It's only one unit, but the unit is not in Mozambique. That's why we are talking about to gradually replace the generator, also to reduce the self-sufficiency in terms of energy supply in the community, because now we rely on the generator that is in another country, a neighbor country, Zambia in this case. So that's why our plan is gradually to replace this dependence. So we are designing a project of 2 megawatts with the battery storage, so that can supply electricity 24 hours per day in the village. So if it's possible, Ivan, I would like to get more information, technical information about the hybrid controllers.
Of course.
So that we can evaluate in detail if we can use this technology or not.
Okay. No
I think
worries.
I would propose, Engineer Isaac, that we can share, by email a bit of details of the project, and then we can together with my colleagues here, we can prepare like a bit of a technical note, or so with some recommendations for your project, which I think is very, very important at the stage that you are now to think carefully about the ideas that could be there. Yes.
Super, Paul. it will be a great opportunity for us to
Yes.
work in close with you.
Excellent. Pleasure.
Yes.
Okay, we still have time for one final question, one last question, if there is one, before we close. No, everything okay? Mr. Antonio Julio Tomas, are you want to participate? Okay, because I see your microphone is on, and I'm not sure if you want to.
Yes, I am here.
Okay, yes, please.
Sorry.
Tell us. Do you have a question? Do you want to ask something or alguna pregunta? Okay, then there might have been a
Tony?
Might have been a connection issue, perhaps.
Tony? Hello, Tony? No.
Okay, never mind. If there are any further issues by email, we can always go back. So it's now 11:15, almost in Mozambique. I think it's now time to close because our colleagues, they all need to go back to their jobs, and all of us here as well. I would like to thank again very much the participation of today's guest speakers, Engineer Imran from Integration in Germany and Engineer Ivan from Azimuth 360 in Barcelona for their valuable contributions today. Thank you very much, guys.
Thank you for the opportunity to be here. It was a pleasure.
You did very well because I teach them, yeah, a lot of more from the scientific or the academic point of view, but I know that it's very important for the colleagues we have in Mozambique to get to know also what is going on in terms of applied projects, okay? And the work that you do with your organizations is very relevant for the knowledge we are trying to share in this course. So once again, thank you very much for your time. And yes, I'll be contacting you to address some of these issues, specifically the question that came from Mr. Tsaba from EDM, which I think it's a very specific one that deserves some good elaboration a little bit in detail, and we can engage with them then separately by email, the technical note. Okay, if that is fine. So thank you very much. Have a good rest of have a good rest of your day, everybody. The session has been recorded, so and we will be editing it and putting it, enabling it for your access, so that you can revisit all that was discussed and was presented. And with that, we will close the session now. So have a good rest of the day. And
thank you very much. And bye bye. It was a pleasure.